Today we are going to create a model of co-regionalisation based on ordinary co-kriging, and we are going to compare this model with a model of regionalisation based on ordinary kriging. And we are going to see how in this scenario, based on contaminated soils, the co-kriging model provides better results on the prediction of the zinc concentration compared with the kriging model. Because the highest residual value in the co-kriging model is 3 times smaller than the highest value that we can find in the kriging model. Also, the scatter plot related to the observed values against the predicted values in the co-kriging model is showing a cloud of points very compacted, and the points are making almost a perfect straight line with a 45 degrees. But in the kriging model, as you can see over here, the cloud of points are pretty dispersed and the regression line is making an angle smaller than 45 degrees. And the last one, because the root mean square error on the co-kriging model is closer to 0, showing a value of 0.06, while the root mean square error of the kriging model is 0.20. Hello and welcome to the third geostatistics course with R integrated in QGIS. The main topic of this course is structural analysis for kriging co-kriging interpolation. This is the 9th and last lesson of this course, and today we are going to be talking about structural analysis for co-kriging. Let's start with some definitions. Co-kriging can be considered as a generalization of the kriging technique, with some specific particularities. It means that all the theory that was used for the structural analysis when dealing with kriging, now it can be used also when dealing with co-kriging. The main difference is that the kriging technique is just for one random function, one variable, and co-kriging is for 2 or more random functions, multiple variables together. Co-kriging allows to use an auxiliary variable together with the target variable to predict this target variable in unsampled locations. The target variable is also known as a main or primary variable, and the auxiliary variable is known as a secondary depending on the number of variables, or more commonly known as a covariables. It is necessary when using the co-kriging technique that the target and auxiliary variables to be individually spatially autocorrelated, and in addition both of them has to be spatially cross-correlated. When these 2 assumptions are covered, the variables are co-regionalized and then can be used to predict the values of the target variable in unsampled locations. Also, it is necessary that the target variable and the auxiliary variable to be linearly correlated. As bigger is the linear correlation between the target variable and its covariables, better is going to be the prediction with co-kriging interpolation. Why to use co-kriging? Sometimes there is a target variable that is expensive or hard to be measured or sampled. Thus, this target variable presents a short sample population with a low density distribution that makes difficult to predict the value of this variable in an unsampled locations using kriging. However, sometimes there is an auxiliary variable, covariable, that is linearly correlated with the target variable that is cheaper or easy to be sampled or measured. This auxiliary variable can present a bigger population and bigger density distribution due to the low cost or low effort to be sampled or measured. Then, with Cokriging, it is possible to use these two variables together to predict the target variable after covering the prerequisites associated with the Cokriging technique. Not always Cokriging is going to be a better prediction than kriging. It is going to depend on the linear correlation between the variables. X scenario for Cokriging. The most common X scenario for Cokriging is when there are two different sets of samples. The first one is a set of samples with the target variable. The second one is a set of samples with the auxiliary variable, where some of the samples are measured together with the target variable, and it is known as a collocated measurements. And the rest of the samples are independent. The target variable used to have a limited density distribution compared with the auxiliary variable. Remember that the auxiliary variable, covariable, has to be correlated with the target variable in both feature and geographic space. Then the covariables must have first a feature space correlation with the target variable, linear correlation positive or negative, a spatial structure, spatial autocorrelation, and the third one, a spatial covariance with the target variable, cross-correlation. Here at the bottom we have an example with the two sets of samples. The red cross is the samples related with the target variable, and the blue circles are the samples related with the auxiliary variable. As you can see, there are some locations where we have both samples, and these locations are known as a collocated measurements. As we said previously, the target variable samples are not well distributed and the number of samples are quite short. But the auxiliary variable, the distribution is pretty homogeneous and the number of samples is bigger than the target variable samples. It is essential when working with Cokriging to have collocated measurements. In that way, we can make a proper linear correlation between the two variables. Now let's see examples related with Cokriging. Then, for example, the first example could be the target variable could be the temperature, and the auxiliary variable could be the altitude. We know, in fact, that these two variables are linearly correlated. We know as higher is the altitude, lower is going to be the temperature. Then, for example, in this case, we can have some stations that are distributed in an area, but we don't have too much stations, right, to measure the temperature. But we can download, for example, a digital elevation model with the elevation of the terrain, and we are going to have a lot of data related with the altitude, because it's going to be a raster file, and for each pixel, depending on the dimension of the pixel, we are going to have a point of data. Then we are going to have a lot of data related with the altitude compared with the temperature. And this digital elevation model with the altitude could be from the satellite information, could be a LiDAR information, and the resolution, right? The pixel resolution of the raster file related with the altitude is going to depend what is the remote sense that we are using, right? But we are going to have a lot of data related with the altitude. And as we know that these two parameters are linearly correlated, we can use the altitude as an auxiliary variable to predict the unsampled locations of the temperature. Another example could be the chloride concentration in soils with the electroconductivity. In this case, for example, to measure the electroconductivity in soils is cheaper than measure the concentration of chloride in soils. But we know as bigger is the concentration on chlorides, higher is going to be the electroconductivity. This is a fact, okay? And these two parameters are linearly correlated. And as I said previously, to measure the electroconductivity in soils, it's much more cheaper. And then we can take a lot of samples with field instrumentation. And then, for example, for the chloride, we can take some samples, send to the lab, measure the concentration of chlorides, and also measure the electroconductivity. Then, for example, at the field, measure the electroconductivity with field instrumentation in the same locations that we take the samples. Then we can calibrate the model with the electroconductivity, just making a comparison between the electroconductivity from the lab and the electroconductivity that we measure at the field. And then we can use the electroconductivity measured at the field as an auxiliary variable, because to measure the electroconductivity is cheaper and we can take a lot of samples of the electroconductivity at the field, right? And it's a good co-Cokriging also in this example. And another example is the groundwater elevation related with the terrain elevation. Sometimes the groundwater flow direction, it's in the same direction as the terrain elevation, but it doesn't happen always. Then this one, it's not a fact. These two, it is a fact. We know already that that one is going to happen. But with this one, we are not sure 100%. Then in this case, when we are not sure 100%, we have to be very careful, assuming that the parameters are linearly correlated, because could be a coincidence, okay? Then in these cases where we are not sure 100% about the relation between the two parameters, we need more samples to verify that one. For example, in this case, if you have the measurement for example, 5-6 wells, and you see that there is a correlation, maybe it's just a coincidence because you don't have enough samples to verify that groundwater flow direction is following the slope of the terrain, for example. Let's go to put an example. Let's go to imagine that we flip a coin 10 times. Okay, then we are going to have 10 samples. And the expectations is going to be 50% heads and 50% tails. But as you know, maybe can happen that you are going to have 10 tails. That is not difficult, or for example, 8 tails, right? Then there is variance. As smaller is the number of samples, bigger is going to be the variance. And for example, if we flip the same coin 100 times, we are going to be closer than to the 50-50%, right? And if we flip that coin 1 million of times, we are going to have a lot of samples, and I'm pretty sure that we are going to be at the 50-50 very close. But with the very short number of samples, anything can happen because the variance is so big. And that's what happened with the covariables sometimes. It looks like they are correlated with the main variable, but maybe it's not correlated. Maybe it's just a coincidence due to the short number of samples. And then we have to be very, very careful with these kind of things. Then if you're asking me how many samples you need to verify the linear correlation between two variables, I'm going to say I have no idea. Every scenario is different. It depends on the context, right? Then as a professional, you have to decide what is going to be the best number of samples to verify that one. Sometimes maybe it's 50, sometimes maybe it's 20, and sometimes maybe it's 100. It depends on each scenario, you know. You have to look for clues to identify the relation between these two parameters, right? Look for other type of information that is going to help you. Sometimes it's really difficult, but you have to make sure 100% that they are linearly correlated, and this correlation it's real. It's not something fake. Now let's go to see the data sets I created to make an example of ordinary co-kriging. Maybe at the future we can make more complex examples related with co-kriging, for example collocate co-kriging or universal co-kriging or co-kriging with anisotropy, but that is not going to be part of this course. At the moment what we are going to do is just ordinary co-kriging. For this example we are going to be working with the Meuse River dataset. In this dataset we have 155 samples with different parameters. We have the X coordinate and Y coordinates, and we have 4 different metals. In this example we are going to work just with the zinc concentration and the lead concentration. We are not going to use the rest of parameters like the elevation, distance to the river, concentration of organic materia, type of soil, land use, etc. We are going to use just the zinc concentration and the lead concentration, and these concentrations are in ppm. We are going to use the zinc concentration as the target variable and the lead concentration and as auxiliary. And what I did is I selected 50 samples randomly from this dataset for the zinc concentration, just to try to emulate that I have one variable, that I have just a very few samples. In this case it's going to be the zinc and it's going to be the 50 samples, and also I have another variable that in this case is going to be the lead concentration with 155 samples. Then the number of collocate samples, that is the samples that I have the measurement of both parameters, is going to be 50 samples. That's the number of samples I'm going to use to establish the linear correlation between these two parameters. Now let's go to see the data sets I created. Then the first one is going to be the 50 samples for the zinc concentration. Then I selected these 4 parameters, the X and Y coordinates in UTM, the zinc concentration in ppm, and I also calculated the logarithmic with base 10 for the zinc concentration. As we are going to see, in this case we have to make the transformation of the zinc concentration because the distribution is not normal. Remember that I selected these 50 samples randomly from the Meuse River dataset. Now the next one is going to be the, let me minimize this one, the 150 samples, 155 samples for the lead concentration. In this case what I did is took all the samples from the Meuse River dataset related with the lead. Okay, in this case we have 155 samples, and also we have the same parameters. We have the X and Y, they are UTM coordinates. We have the lead concentration in ppm and also the logarithmic with base 10 for the zinc concentration in ppm. And the last data set is going to be related with the collocated samples for the lead and the zinc. Let me open this one, and as you can see, in this case we have 50 samples, okay, and we have these parameters, the X and Y coordinates in UTM, the lead and zinc concentration in ppm, and the lead and zinc concentration in logarithmic with base 10, and that's the collocated samples. That's the 3 data sets I have for this project. Just to let you know that I'm using the Open Office. If you want to download this free and open source software, just go to the GeoRGB community at gscourse.online, then go to resources, and here there are different icons. Just make sure you select this icon, click here, and then you can download this software for free. And also for all these data sets, I'm going to put these data sets on the course. then you can download that information. Then go to the third geostatistics course, get enrolled, start the course, then go to the lesson number 9. This one is number 8. I didn't load the number 9 yet. Then select the lesson, and here, as you can see at the bottom, there is attachments that you can download the documents. Okay, I'm going to add here the scripts, the data sets. Then you can download this information and replicate the results I get on this exercise. The next step is to load the datasets in QGIS. Remember that to load the spreadsheets, the format has to be CSV, as you can see over here. Okay, then I open already the QGIS, press this option over here, select delimited test, and then look for the files. It's going to be this folder over here, this one. First, I'm going to load the 50 samples for the zinc concentration. Open. Then make sure you have selected this option over here, and make sure to select the proper coordinate reference systems. In this case, I'm going to change the coordinate systems, and what I want is the code 28992. Is this one over here, and OK. Also, make sure you have selected point coordinates, because we have geometry X and Y. Then select this option and make sure the X is with X and Y is with Y. Okay, then add, OK, and close. And now I'm going to change the color of these ones. Properties for a red color. Symbology is going to be this one, and red color. Apply and OK, and also to put the satellite imagery from Google. That is going to be this one over here. Now I'm going to add the 155 samples related with lead. Then select this one, and it's going to be this one over here. Open. Is going to be the same steps. This one is good, the coordinates is good, and everything is good. Then add and close. And in this case, I'm going to change the color for a green one. Maybe color like this one. Apply and OK. And I'm going to put this one at the bottom over here. Then, as you can see, this one is the 50 samples that I selected randomly, and that's for the zinc concentration, and it is the target variable. And then the other one is the lead, and we have the full set of samples, that is 155, and this one is going to be the auxiliary variable. Now I'm going to add the collocated samples. Then this one here, this one, and is this one over here. Open, and everything is good here. Add and close. And if we take these ones, this one is the collocated samples, okay, where we have the target and the auxiliary measured at the same point. Now I would like to show you how the data set it's now following a normal distribution for the zinc concentration, and that's the reason because we need to do a transformation of the data. I'm not pretending to do a full exploratory data analysis. We did already at the courses, at the first and second course with the univariate analysis and bivariate analysis. But in this case, just I'm going to do the histogram. But first we have to export all these data sets as a shapefile. Then select the data set with click right on your mouse, then go to export, save feature as, then the name of the file is going to be the same. Let me copy the name of the file, then rename layer, and I'm going to copy all this name, copy and now I'm going to export. Export, save as a feature. Going to put this name, but save here in this folder, inside this folder. Then paste here that name, save file, save, and the rest of the things is good, and okay. Now we have the shape file and we can remove this one. Properties, you can see that one for the information is a delimited text, but for this one, properties, information is a shape file. Then we can close this one, remove layer, okay. And I'm going to do the same for the sync and for the collocated samples, but I'm going to pass the video faster. Now I have all the datasets in save file. I need that one in order to use the R scripts. Then the first thing we are going to do is the histogram for the zinc concentration in ppm. Then go to R. That script comes from the first geostatistic course and is the script number 5. Is this one, no, number 5, number 6. Then double click to open and select the data set. In this case is going to be the zinc concentration. The parameter is going to be the zinc. First we are going to do with zinc and then we are going to do with the transformation to see the difference, right? Then for the X is going to be the zinc concentration in ppm. For the Y is going to be the number of samples. Title of the graph is going to be histogram. Subtitle is going to be raw data. Here we are going to have the minimum concentration. Here we are going to put the maximum concentration. Then we are going to calculate what is the difference, and then we are going to divide between 7. That is going to be the number of intervals or the number of bins in the histogram. Then I'm going to add the information, but I'm going to pass the video faster. Now we are going to add the minimum value, then go to the attribute table, order this one, and the minimum concentration is 113 and the maximum concentration is 1672. Then this one here is going to be 1672. This one is going to be 113, and now we are going to calculate the difference with the calculator. Then calculator here, and it's going to be 1672 less 113, this number divided by 7, because it's the number of bins we want in the histogram. Then I'm going to copy this value here, select all, and I'm going to paste over here. Paste, oh sorry, I didn't copy. Select, copy, and paste. And then we can run. And that's the histogram for the raw data. As you can see, we have a skewness to the left, okay? Then it's pretty clear that the data is not following a normal or Gaussian distribution, you know, with a bell shape. It's not this case, because most of the data is close to 0. As you can see, 22 samples are in this interval, okay? Then for bigger than 1000 ppm, we have just 3 samples. Now we are going to do the same histogram but with the data transform. Then go here, go here. Here then is going to be transform data. Transform data, and here is going to be the zinc concentration, but it's going to be the log 10 for the zinc concentration in ppm. Then the minimum value, let's go to the attribute table. Here select the minimum value, copy this one, copy, and then let's go to paste over here, and let's go to do the same for the maximum value. Too many things open here. Minimum maximum is this one, copy and paste over here. Sorry, paste over here. Let's go to make the difference, then paste, take the calculator, let's put 0 here, paste this one, less the minimum value is this one. Let's go to copy, copy, go here, Control V to paste. Then equal, first we have to divide it between 7, and then select all, copy and paste here for the interval, paste, and then we can run this one. Double click to open, and the problem here is that we didn't select the proper parameter, that in this case has to be the logarithmic with base 10 for the zinc concentration. Then run again and double click to open. And as you can see now, the distribution improved a little bit. Okay, it's not the best, but it's more symmetric. Okay, we don't have the big skewness as we have here. Then that one is better distribution. The point is that the semi-variogram function, it's not a parametric function. It means that we can use a distribution that is not normally distributed. But if the distribution is close to the normal, better is going to be the results, because the mean value of the data set is going to be representative of all the data. Okay, what happens sometimes if we have a big skewness is that the mean value is not representative of the data set. Now I am going to do the histograms for the lead concentration, but in this case remember that the number of samples is 155, then we can add more bins to the histogram. In this case we are going to add 12 bins. I fill already all the information. I selected this data set for the 155 samples for the lead. I selected the lead parameter. Here we have the lead concentration in ppm. At the y-axis we have the number of samples. The title of the graph is going to be histogram. The subtitle is raw data. The minimum value, if we go here, sorry, I take the minimum value for the wrong one because it's the logarithmic with base 10. I have to take this one, 37, and the maximum 654. 37, 654. Then here is going to be 654, 654. Here is going to be 37, 37, and then we have to make the difference with the calculator. Let me open the calculator. Then it's going to be 654 less 37 equal divided between 12. That's the number of bins we want on the histogram. Then copy this one, select all, copy and paste over here. Paste and run. Double click to open. And as you can see, in this case, again, we have a big skewness to the left, okay, with most of the samples located at the first bin. Now we're going to do the same, but for the logarithmic with base 10 zinc lead concentration. Then go here, let's go to change the parameters over here. This one is going to be log 10. This one is going to be transformed data. This one is going to be the log 10. And then we have to see what is the minimum and maximum value. The minimum is this one, copy. Paste over here. Control C, Control V. And for the maximum, go to the attribute table. I have too many things open here. Open. The maximum value is this one. Copy cell content, go here, paste over here, Control V, and now we have to make the difference with the calculator. Okay, this one, copy the value over here, paste, minus this value over here, Control C, and we can paste over here, Control V, equal, divided between 12. Then we can copy this one, select all, copy, and paste at the interval. We want 12 intervals, and run. And as you can see over here, the distribution of the data improves a lot again. Okay, it is important in this case that when we are going to compare both variables, we have to do that ones in the same dimension. Okay, if we are doing the logarithmic with base 10 for the zinc concentration, then we are going to do also the same for the lead. In that way we can compare both variables in the same way with the log with base 10. Okay, also we can do the histogram for the lead with 50 samples. Is this data set here, this one. Open the attribute table. Here we have the collocated samples for the lead and for the zinc. We can do also the histogram for the 50 samples of the lead, but the result is going to be the same. Okay, then I'm not going to do it, but it's something that if you want to do, just do it, but the result is going to be the same. We are going to have left skewness, and then when you make the transformation, the data is going to improve. Now let's go to see the first script for today. And this script is going to be related with the feature space linear correlation, and we are going to use the Pearson's parameter. Then create a new script. I'm going to paste what I did already, paste, and make this one bigger. We know about all these things already. This one is going to be just a scatter plot between the two collocated measurements, the zinc concentration and the lead concentration with log 10. And then we are going to calculate the Pearson's coefficient. That is for linear correlation between two variables. Then I'm going to cut this one here. Cut. Then I'm going to remove these two lines over here. Save as with this name, paste, and save. And then close. And we can run that script. That is number 46. Then structural analysis, double click, and we are going to select the dataset where we have the two collocated samples. Then for the X is going to be the lead, and for the Y is going to be the zinc for both of them log 10, okay? Then x is going to be the logarithmic with base 10 for the lead concentration. In ppm, and for y is going to be the same but for the zinc. Then copy, paste, and let's go to change that one for zinc, and the title could be the feature space linear correlation, Pearson's. Paste, and here I'm going to indicate that the data is transformed. Transform data. And then we can run. And what we can see in this script, that the Pearson's correlation, the value is so big, right? It's 0.96. For a value of 1, it is indicating at perfect correlation. But in this case, it's almost perfect, right? Because it's almost 1. Then it's indicating that the linear correlation is really good for these two values. And we can see the graph over here. Let me make this one bigger. Important things related with this graph. First is that all the dots are making a line. When they are making a line is when we can use the Pearson's coefficient correlation. We was talking about this parameter in a different lesson. It was the lesson number 2 for the second geostatistics course related with bivariate analysis. Then if you want to have a clear explanation about the Pearson's coefficient, you can check that lesson. Also, another very important thing is all these samples are collocated. It means that the value for the lead concentration and the value for the zinc concentration has been measured at the same location, okay, for each of these dots. And that's very important to have a real linear correlation between the data. Also, in this case, both parameters are in the same unit, you know, log 10. That's very important. In addition, we know that these two parameters were transported by the same mechanism, that it was the flow of the river. And also we know that the contaminant, both of them are associated with the industrial activity. Then they have the same origin. And as we are going to see later, both of them has a very similar semi-variogram functions. And all these things together are indicating that these two parameters are correlated. I don't have any idea about if there is any correlation about the zinc concentration and the lead concentration. I don't know, but the data is showing me that they are correlated. Then I can say that the lead concentration is covering my first assumption, because the covariate, that is the lead concentration, has a feature space correlation with the target variable, that is the zinc concentration, because they have a positive linear correlation, and the value of this linear correlation is really big, it's close to 1. Then the lead concentration, it's a good parameter to predict the zinc concentration in the unsampled locations using the Cokriging technique. But also we have to make sure that we are covering the other assumptions. Let's move on to the second and third assumption. The cross-variogram. The number of variograms that has to be modeled to perform the Cokriging technique comes from this formula, where n is the number of variables, random functions. For the simplest case, there are two variables. One is the target variable and the other one is the auxiliary variable. In this case, it is necessary to model three different variograms. Two direct, that is the target and the auxiliary variables, and one cross-variogram, that is the target and the auxiliary variable together. Here we have the variogram function for just one random variable. That's the function that we are going to use when we are dealing with kriging. And here we have the variogram function that is the cross-variogram that we are going to use when we are working with two or more random functions. It means that we are going to work with two or more variables. And as you can see, the formulas are pretty similar, right? This formula is a square here, but it's a square but in self, right? And here what we have is the cross of the two variables. And that is the difference between these two functions. We are going to use this one with kriging because it's for just one random function. And for co-kriging, we are going to use both. This one for the direct variograms, for the auxiliary and for the target variable, and this one to do the variogram together between the target and the auxiliary, right? And this case is just for two random functions, but it could be for a number bigger than 2, okay? The simple one is going to be 2, but here we can have 3, 4, it depends on the number of covariables you want to use to do the cross-variogram. One important thing is that there are no models for the cross-variogram function, like the models we have for the variogram function. I mean the Gaussian, the spherical, the exponential model, etc. All the authorized models. But as this function, the cross-variogram function, is very similar to the variogram function, to this function, we can use the same models to fit on the experimental cross-variogram, the spherical, the exponential, etc. However, the cross-variogram function can be negative. It depends on the relation between the two variables. As we saw here, the relation is positive, then the cross-variogram function in this case is going to be positive. But if the relation is negative in this direction, then the cross-variogram function is going to be negative. But that is not a big deal because we have to multiply just by -1 and then we are going to have the function positive. And that's what most of the softwares are doing automatically, okay? But we have to be aware that in this case, the cross-variogram function can be negative. And the reason is because the relation between the two variables is negative. But for the variogram function, the result is always positive, never is going to be negative. And that's another difference between these two functions. When we are working with Cokriging, it is very important the linear model of co-regionalisation. Here in this lesson, we are not going to go very deep in this concept. If you want to learn more a little bit about this model, just follow this author and you are going to get a lot of information. Here we are going to see just a very short summary about this model. Then, when we are working with just one random function, it means that we are using this formula over here. And it is possible to fit an authorized variogram model on the experimental semi-variogram. Then these authorized models are the spherical, the exponential, the Gaussian, and etc. It is guaranteed that the kriging system is positive definiteness. And this condition to be positive definiteness is necessary in order to have a valid model that will provide valid results with kriging. However, when we are working with two or more random functions, it is necessary to fit the model in the direct and cross-variograms simultaneously. But even when it is using the authorized models, the positive definiteness is no guarantee in the Cokriging system. Then, in order to have a valid model where the Cokriging system is positive definite, it is possible to use the linear model of co-regionalisation, LMC, where all the models, direct and cross, have the same shape and range, but they can have different partial zero or nuggets, and that is very important. Then it means when we are fitting the model in the direct variograms and also in the cross-variograms, all of them, all the models has to have the same shape and also the same range. The only thing can be different is the partial seal and the nugget. Then when we are saying the same shape, it means that we have to fit the same model for all three experimental semi-variograms. It means that for the experimental direct variogram we fit an spherical model, then we have to fit an spherical model also for the cross experimental semi-variogram, because all has to have the same shape, and it means the same model. Then just to make a summary, let's go back here. And when we are dealing with kriging, we are going to use this variogram function, and when we are fitting the model on this experimental semi-variogram, we have not to be worried about the positive definite of the kriging system, because that is guaranteed when we are using the authorized models. For example, the Gaussian, the spherical, exponential, etc. But in this case, that one is not guaranteed. Then, in order to have a definite positive co-Kriging system, what we have to do is to use the linear model of co-regionalisation. And it means that in this case, all the models that we are going to fit on the experimental semi-variograms has to be with the same shape and also the same range. And when it's the same shape, it means it has to be the same model. Then if we are using an spherical model for the direct variogram, we have to use the same model for the cross-variogram. That's something that we have to do in order to guarantee the positive definite co-Kriging system. The partial seal and the nugget can be different, but not the shape and the range. Then we can say that the linear model of co-regionalisation is very restrictive, and it makes the co-Kriging technique difficult to apply in most of the scenarios. The linear model of co-regionalisation can be applied for two random functions or more, but the most common case is for two, as we saw in our example. Also, the number of structures can be 1, 2 or more, but the most common case is 2. The variogram model associated with the nugget, and the other structural variogram model that could be the spherical, the Gaussian, the exponential, etc., or any combination of the authorized models. Here I said 1 because maybe in our structure we don't have nugget, and if we don't have nugget we are going to have just one structure. But the most common thing is 2, right? One structure associated with the nugget effect and other structure associated with one of these models or any combination of these models, or other models that are also authorized but they are not here. I know at this point all these things looks pretty abstract, but when we are working with the real example, everything is going to be pretty clear. Now let's go to move on to the next one. That is this one, the linear model of co-regionalisation. This is an example for two random functions with two structures. Then in this case, the three variogram models are the same, as well as the range. Only the semivariants may be different, the nugget and partial seal. Remember that from here, let me make this one bigger. This is just an example. From 0 to here, we have the nugget effect. That's the first structure. And from here to here we have the second structure, and this structure is associated with the, in this case, with the spherical model. And the spherical model has all these variants, all these semi-variants from here to here, and the nugget effect has the semi-variants from 0 to here. Then in this matrix, that is the matrix associated with the linear model of co-regionalisation, what we have is a matrix of the semi-variants for all three models. Okay, this is an example for two random functions. Okay, and with two random functions we have to model three different variograms, two direct and one cross-variogram. Even here we have four. The reason is because these two are the same. These ones are associated with the semi-variants of the cross-variogram, okay, but they are symmetric. And this one is for the, for example, for the main variable. This one could be for the auxiliary variable, and this one is the main variable with the auxiliary variable, and this one is the auxiliary variable with the main variable. But these two are symmetric. Then what we can have for the semivariants is separate the semivariants by the structures, right? This one is the structure associated with the nugget, and this one is the structure associated with the model, spherical, exponential, any model, right? Any authorized model. Then if we plus the both structures, we are going to have the total semivariants. And the total semivariance is going to be the seal. Remember, right? That one is going to be the seal. And the seal is the nugget plus the partial seal. And the partial seal goes from here to here. And the nugget goes from here to here. Later we are going to see this matrix with real numbers from the example we are working. That is the general case for two variables with two structures, but it's just to have an idea how it works. Then in order to have this matrix positive definite, we need this value and this value be bigger than 0. Is this diagonal over here. This one has to be bigger than 0, this one has to be bigger than 0, this one has to be bigger than 0, and this one has to be bigger than 0. That's what we can see here. And also for this value over here and for this value over here, what we need is the root square of the diagonal. This diagonal has to be bigger or equal to this value over here, and the same for this matrix. And when this happens, this matrix is going to be definite positive or positive definite, okay? And if it is not possible to cover this assumption, this one over here, then it is necessary to adjust the values of the parameters, then adjust the model to have different values over here, because when we feed the model on the data, we are going to have a value for the nugget and we are going to have a value for the partial seal. Then if we want to have different values for the nugget and for the partial seal, what we have to do is move the model to have a different values, right? And that's what we have to do here. If we are not covering this assumption, we have to adjust the values of the parameters associated with the nugget effect and the partial seal, or change the model also. Maybe if we change the model, we are going to have better values in order to have a positive definite system. This one, this matrix, okay? It means that sometimes it is not possible to have the best fit model on the experimental semivariograms. Then it is necessary to sacrifice the model to perform the Cokriging. At the end, as better is the linear correlation between two variables, this linear correlation that we saw here with the two variables, as better is this linear correlation, as better is the linear correlation between the two variables, easier is to cover this assumption over here. It is necessary to understand that this assumption is very restrictive, okay? And sometimes co-kriging is not providing better results than kriging because of the restrictions. Then sometimes we have to model the experimental semi-variogram with a model that doesn't fit really well on the data, but we need to fit in that way in order to have a proper values for the matrix, for the linear model of co-regionalisation. And because of that one, maybe we are not going to get better results than the kriging interpolation, okay? Then you don't have to be very worried about all this stuff, because with R, it is possible to automate all the process related with the linear model of co-regionalisation. Then we are going to put the models, and the software automatically is going to fit the model that covers this assumption. And that's really well, because then we don't have to be moving the model to fit on the experimental semi-variograms. We are going to see that one later, but you are going to see that it's pretty easy, and all the process is automatic with R, okay? Also, one more thing is in this case we put just two structures, but sometimes we have a combinations where we have more than two structures. Then the point is just to add the extra structures we have and also verify these conditions, the ones I set over here. Or maybe sometimes we don't have the nugget, then we can remove this structure and work just with this structure to verify the positive definite of the system. Well, that's it for the theory. Now we are going to work with the scripts to analyze the structure related with Cokriging. First, we are going to do the structural analysis related to the target variable. In this case, it's going to be the logarithmic with base 10 for the zinc concentration for these 50 samples over here. We are going to go very fast because all the scripts and all the process related with that scripts is already explained in different lessons. Then the first script that we are going to run is going to be the omnidirectional semi-variogram cloud. With that graph, we can identify if there is any outlier. Is this one over here, the number 1? We are going to identify if there is any outlier in the data set, and also if there is any trend, okay? Then the parameter, first we have to select the logarithmic with base 10 for the zinc, for the 50 samples. The parameter is going to be this one. The cutoff, at the beginning I want to see all the extension. Then I'm going to put 4,500 meters. The label X is going to be the lag distance. Label Y is going to be the logarithmic with base 10 for the zinc concentration in ppm. The title of the graph is going to be the omnidirectional semi-variogram cloud for the zinc concentration. And the subtitle is going to be transform data. I fill already all the information, and now we are ready to run this script. Remember that this script is part of the lesson 2 of the third geostatistics course. You are going to find in that lesson all the things related with this script. Now we can open the graph. The omnidirectional semi-variogram cloud is very good to identify if there is any trend on the data. As you can see, the dots are not follow any specific direction. Looks like they are pretty randomly distributed, and that is a good thing, indicating that there is no trend on the data. But also later with the experimental semi-variogram, we are going to verify that one. Another very good thing with the omnidirectional semi-variogram cloud is for identifying if there is any outlier on the data. You know, looking for dots that are very far away from the main cloud of points. In this case, I can say that I cannot see anything special related with the outliers. Then I'm assuming that in this data set there is no outliers. Now the next step is to see the general structure of the data. Then to do that one, we are going to use the script number 10, and this script is part of the lesson 4th of the 3rd geostatistic course. Then we are going to select first the shapefile layer we want, that is the 50 samples for the zinc concentration, then the logarithmic with base 10 for the zinc concentration. The cutoff, again, we want all the extension, 4,500 meters. Then for the lag distance, as this one is going to be a general view of the structure of the data, at the beginning we can put a bigger lag distance to have a general view. But then for the next graph, we are going to be more accurate, okay? Then at the beginning, I'm going to add 200 meters. For the label X is going to be the same as this one, lag distance in meters. Then I'm going to copy and paste over here. And the same also for the label Y. I'm going to put the semi-variance for the lag distance, the semi-variance for the logarithmic with base 10 for the zinc concentration in ppm. Title of the graph is going to be experimental semi-variogram for the zinc. Subtitle is going to be transform data. Then this script is ready to be run, and double click to open. Important things related with this graph. First, we have to understand that this experimental semi-variogram is omnidirectional one. It means that we use all this data. Let me move this one over here. We use all the data associated with all the points because there is no any specific direction, okay? We are using all the data to make the representation of this experimental semi-variogram. Then this experimental semi-variogram is going to be the best estimated because it's the one with the maximum number of data points, okay? Here, as you can see, we have the lag distance for every 200 meters. And also the total extension is 4,500 meters. It is covering all this extension, okay? 4,500 meters. Also, the data is not showing any parabolic trend. That is indicating that the data is covering at least the intrinsic hypothesis of stationarity. Then the data is stationary. Also, the data is showing a good structure because, as you can see, the experimental semi-variogram is growing up over here, then reaches the seal and then goes down. Then we have over here a very small negative effect compared with all this structure related with the partial seal, okay? As the negative effect is very small compared with the partial seal, then we can say that we have a really good structure in this data. We are going to see this structure more clear when we model the experimental semi-variogram. Now it's time to create this graph but more accurate because I don't want to see all this data. This data is not showing any spatial continuity. The area that is showing the spatial continuity is this area of the graph where the experimental semi-variogram is increasing and then reach the seal. That is the correlated area of the graph, and I want to use just this area to fit the model. Then what I'm going to do is approximately select what is going to be the range, that in this case is going to be around 1,000 meters. And then I'm going to make the lag distance a little bit smaller in order to have more data points to later fit the model in that experimental semi-variogram. I would like to have at least 10 points at the correlated area of the graph to fit the semi-variogram model. But also what I want is to have each lag distance with a good representative number of pair of samples. I don't want to see very low numbers over here. Then my decision is going to be a lag distance of 125 meters and a cutoff of about 1,500 meters. With that cutoff, I'm going to guarantee that I'm covering all the correlated area of the graph. Then to do that one, we are going to go again to this, not this one, I can close this one, but I'm going to use again this script to do that one. The only thing I have to do is change just the cutoff here, 1,500 meters, and here for the lag distance, 125 meters. And then we can run this script again. Double click to open, and we can make this screen bigger. Now what happened for the this lag distance, we have more data points to fit the model, but the problem is that each lag distance now has less pair of samples. But this number is good enough to fit the model. This one is pretty low, but that's pretty normal that the first lag distance is very short in numbers. But we are not very worried with that one because these points over here, they are really well estimated. It's better if you have 100 pair of samples, but with 50 it's not that bad, considering that we have just 50 samples, right, on the data set. Okay, let's go to see the graph again. And this one is going to be the experimental semi-variogram that we are going to use to fit the semi-variogram model. Now, the next step is to model this experimental semi-variogram. Then to do that one, we are going to use the script number 19, model semi-variogram omnidirectional. Then double click. And this script is part of the lesson 5 of the third geostatistics course. Then you have in that lesson all the information related with the models, okay? Then to fit the model, we are going to select the proper shapefile. The parameter is going to be the logarithmic with base 10 for the zinc concentration. The cutoff is going to be the 1,500 meters, as we did for the experimental semi-variogram. Over here, we are going to add the same values. Then the lag distance is going to be 125 meters. We are not going to be very worried about the partial seal. This parameter is the partial seal, it's not the seal. Then maybe I can change this one over here, edit. Well, you know how to change that ones, okay? But you have to put here partial seal, that is a mistake. Then this value could be approximately 0.1 because the model is going to fit on the experimental semi-variogram automatically. And as you can see, the approximately value is 0. Here we have 0.1, is going to be around 0.25, something like that. Then you can add any approximately value over here. We are going to select the spherical model. The range is going to be approximately, again, 1,000 meters. The nugget, it's approximately 0.01. The X is going to be the same as here. Lag distance. Copy. Paste over here. For the Y is going to be the same as this one. Copy and paste over here. And for the title of the graph is going to be Theoretical Spherical Semi-Variogram Model. And subtitle is going to be Transform Data. Then we can run this script. And here, as you can see, we have the values for the structures. First, we have the value for the Nager effect, and the range in this case doesn't have any range, it's 0. And at the bottom we have the structure associated with the spherical model. Then we have a partial seal of this value, and we have a range of this value. Now we can see the graph. Double click to open. And this is how the software fit the semivariogram model on the experimental semivariogram. And this fit was automatically. You can fit also the model manually, that it's explained already in the lesson number 5, but in this case we are going to use the automatic fit. Then, as you can see in this graph, the target variable, that is the zinc concentration, is spatially autocorrelated, okay? And we need that one. Remember when we was doing the introduction, we say here it is necessary when using the Cokriging technique that the target and auxiliary variables to be individually spatially autocorrelated, okay? And that's what we can see over here, the autocorrelation of the target variable. Also here we can see the structure, and we can indicate that the structure is good. We have a very small Nager effect compared with the partial seal. That's a very good structure, okay? Now we are going to do the structural analysis for the auxiliary variable, because again we have to verify that the auxiliary variable is also spatially correlated. We can see this one over here, and also I indicated over here, right, how to select a good covariable. And the second assumption that we have to cover is a spatial structure, spatial autocorrelation of the covariable. And that's what we are going to do now with the lead concentration. Then first we want to do the semivariogram cloud for the lead concentration. In this case we want this data set with the 155 samples, then the logarithmic with base 10 for the lead. Cutoff is going to be all the extension. All these things are going to be the same as we did for the logarithmic with base 10 for the zinc concentration. Label in this case is going to be the same, lag distance. Copy, paste over here. For y is also the same, copy, paste over here. Title of the graph is going to be omnidirectional semivariogram cloud for the lead, and subtitle transform data. Then we can run and double click to open. And as you can see, the omnidirectional semivariogram cloud looks pretty good. And we can move to the experimental semivariogram. Then it's going to be number 10. Double click to open. This one, this data set is good. The parameter again is this one, 4,500 meters to see the general structure. Then 200 meters for the lag distance. The label X is going to be the same. Control C, Control V. This one for the Y, Control C, Control V. Title of the graph is going to be Omnidirectional Experimental Semivariogram. And subtitle is going to be the same as this one. Copy and paste. And we can run this one to see the general structure of the data, right? Then double click to open. And again, this one doesn't show any trend on the data, any parabolic trend. Also, the data is reaching the seal around here, around 1000 meters, then goes down. The structure looks pretty good. And also in this case, as the data set for the lead, let me move all these ones to see the samples related with this data set. Okay, I have too much things open. Maybe this one, well, let's go to keep it. But for the lead, we have a lot of samples. We have all these set of samples, right? That is the reason, because when we saw the omnidirectional semi-variogram cloud, we can see a lot of points now, because the number of pair of samples now, it's a lot compared with the sync data set, right? With this one that it's just 50 samples. Then also the experimental semi-variogram here, the omnidirectional one, is really well estimated, because now we have a lot of pair of samples for each lag distance. Now, as we did for the sync, what we are going to do is make a short lag distance in order to have more data points on the correlated area of the graph. Okay, then let's go here. I believe it was this one. Okay, I cannot see that one. This one, omnidirectional, I can close this one. I want to keep the model because I want to know the values. I can close this one. And now we are going to modify this one. Then I'm going to add 1500 meters. Also the lag distance in this case is going to be 125. We want to keep the values pretty similar in order to compare the target variable with the auxiliary variable, okay? Then that's it. We can run this script. And now let's go to see how it looks like. As you can see, this experimental semi-variogram, it's really well estimated because you have a lot of pair of samples over here, right? Compared with the sync one, here we have just around 50-60 pair of samples for each lag distance. But in this one, for each lag distance, you can see for the first one we have almost 100, right? But for the next one, 400, 500, 600. That's really good one. As you cannot see well the title, you can modify the script and make these letters smaller. If you see the video number 5 related with the lesson for the variogram model, you are going to see how to do that one. And now what we are going to do is add or fit the model on this omnidirectional experimental semi-variogram. Then to do that one, we are going to use the script 19. Is this one, model semi-variogram omnidirectional. Then this shapefile is good. The parameter is going to be this one. Cutoff again 1500 meters. Lag distance 125 meters. Sorry, 125. Again, this one has to be the partial seal, okay? Partial seal, not the seal. And the value it's approximately because the model is going to be fit automatically. Spherical. You can try different models, but I know that in this specific case, the spherical model is the best, okay? Then the range is going to be 1000. This value it's approximately because the model is going to be fit automatically. Then 0.01. The A label X is going to be the same as this one. Then Control C, Control V over here. And the same for this one. Control C, Control V. And for the title, we are going to use the same as this one, theoretical semi-variogram model. Control C, theoretical spherical semi-variogram model for the lead. See, I didn't copy. Okay. No, this one. Control C and Control V. And this one is transform data. And here we can add lit if you want. And then run. And here we have again the parameters for the structure of the model. Then we have this nugget effect over here without any range. And we have this partial seal for the spherical model. And also here we have the range for that model. As you can see, if we compare these two values, we have the same model. That's very important because we need the same model. That's no, not this one. Model, this one. Here for the sync parameter, what we have is a range of 1,162 meters, and for the lit, the range is a little bit different. It's 1,000 meters, right? But in general, we can say that they are pretty close. Then that one is good. For the nugget and for the partial seal, it doesn't matter if they are different. The important thing for the co-kriging is that the model has to be the same, and in these cases we have the same model for both variables, and also the range has to be the same, okay? And we have very approximately values, and that's good. And we can have the same model because both semi-variograms are pretty similar. If we take a look of this one, the distribution of the data allow us to fit the spherical model, and that's what happened also here, right? As the structure of both semi-variogram models are pretty similar, we can fit the same model, as you can see. Okay, if the structure of the data is pretty different, maybe it's going to be difficult to fit the same model. Now that we know that both variables are linearly correlated and both variables have autocorrelation, they have a structure and the structures are pretty similar, then we can fit the same model, and also we have approximately the same value for the range. Now we can go to one step further and see how it looks like the cross-variogram, because that's the next thing that we have to cover, right? Then we already see that the auxiliary variable and the target variable both are spatially correlated, but now we have also to verify that both of them have also the spatially cross correlation, and that's what we are going to do now. Now we are going to see a script to do the experimental cross-variogram. Then create new script. I'm going to paste what I did already, and let's go to make this one bigger. We are going to call this script as a number 47, and it's going to be omnidirectional experimental semi-variogram for co-regionalisation. This one is the cross-variogram, okay? You can put any name. I put this name, but you can change, okay? It's up to you. Then I'm going to cut this one. Cut. I'm going to remove these two lines, delete and delete, and I'm going to save in this folder. Paste. And for all these things, we know already how it works. We are going to use these libraries. Here I define the main variable and the auxiliary variable, or the target variable and auxiliary variable. And here you can see the script to create this variogram. As you can see, we are going to create the first object with the main variable, okay? And then we are going to create a second object, as you can see over here, where we are going to add the first object, that is this one. Then in this object, we are going to have the two semi-variograms. Then in this object, we are going to have the two semi-variograms, one associated with the target variable, and the other one that is going to be all this one associated with the auxiliary variable. And it is interesting that for each of them, we are using different layers. As you can see, for the target variable, we are going to use this layer that we call layer target. And for the auxiliary variable, we are going to use the layer auxiliary. Because as you remember at the shape files, we have these two different layers, right? One is with the target variable, with the zinc concentration, and the other one is the auxiliary variable with the lead concentration. And that's what we are putting over here. Then in this line, we add the final cross-variogram, that is the summation of these two variograms, and then we add these two lines related with the cutoff and the lag that we want for this semi-variogram or cross-variogram. And then I added this one to print the results on the screen, and this one to see the graph. Then at the moment we are going to leave this one to see the value for the pair of samples for each lag, but we can put here false. This T means true, that you want to see the numbers, but if the graph is very annoying because there are too much numbers and you cannot see well the graph, you can put here false, just one F, and then the graph is going to remove the numbers. Let's go to see that one. Then let's go to close and see the cross-variogram. Then go here, structural analysis. We say that is number 47, this one, double click to open. Then the layer target is going to be the zinc for the 50 samples. The auxiliary layer is going to be the 155 for the lead. The target variable is going to be the logarithmic with base 10 for the zinc concentration. The auxiliary, the logarithmic with base 10 for the lead. The cutoff, we are going to put here the 1500 meters, and for the lag distance 125 meters. And I added these two sections to see on the graph and also on the data what is zinc, what is lead, and what is the cross-variogram. Okay, then here I'm going to add zinc. You can add any name, lead, and then we can run. Then as you can see at the screen, we have print all this information. This one, I mean from here to here, is for the cross-variogram, okay? This one is for the lead variogram. As you can see, lead over here. And the last one is for the zinc variogram. Then we are going to see these three variograms at the same graph. Double click to open, and this one is the result. As you can see, zinc, lead, and this one is the cross-variogram. We already did these two. We saw, we fit also a model, but now we have also the information here. But the important thing over here is the cross-variogram, that is this one. And you can see also the number of pairs you have for each lag. And as I said previously, if you want to remove the numbers because you cannot see well, just go to the script, go here to the edition, edit script, put here a false because you don't want to see the numbers, false, and then save and run the script again. Let me show you. And now you are going to see now the things more clear. And the important thing in this graph is that the cross-variogram has a structure also. That's the important thing because it has autocorrelation, and that's one of the assumptions that we have to cover. As we said over here, and in addition, both of them have to be spatially cross-correlated. And that's what we can see over here, the structure. They are spatially autocorrelated because they have a structure. They have the Nagel effect over here, and they have the partial seal from here to here. And also, as we saw over here, the cross-variogram is very well estimated because we have a lot of pair of samples. As you can see, 400, 400, 357, 330. There are a lot of pair of samples for each lag, and it means that it is very well estimated. Also, with this graph, we can make an idea about if the three models, if the three experimental semi-variograms, they are going to have the same model. It is possible to fit the same model in all of them. Then with this experimental semi-variogram, we can have an idea, right? This one and this one are pretty similar. This one is a little bit different, but looks like we can fit the same model. And also in all of them, we need to have the same range, and looks like they have the same range, right? Approximately. And that's the point when we are doing co-kriging, fitting the same model in the three experimental semi-variograms and also have the same range. Again, the nugget and the partial seal can be different, but not the model and not the range. Now we are going to see another script. It's not pretty useful, but I would like to add this one here. It's just to see the three experimental semi-variograms together. Paste is going to be the number 48. At the other example, we was using just gstats to plot the graph. In this case, we are going to use ggplot. As you know, with ggplot, we can make graphs that are more nice. Then cut this one here, remove these two lines, and save with that name. Paste, save. I call this one omnidirectional experimental semi-variogram co-regionalisation number 2, okay? Then save. And this one, it's the same, but it's made with ggplot. Then close this one here, and let's go to run that script to see how it looks like. Structural analysis, number 48. Double click to open. Again, this is the target layer. This is the auxiliary layer. The target variable is this one. The auxiliary variable is this one. The cutoff is 1,500 meters. We are going to add the same information. Then this one is 125. Here is going to be at the x lag distance. For the y is going to be the semi-variance for both parameters. And the title of the graph could be, I don't know, cross-variogram or co-regionalisation variograms, whatever, right? And subtitle could be transformed data. I'm going to add this information, but pass the video faster. Then now we can run this script and double click to open. Now we can make this screen bigger. As you can see, this graph could be very annoying because there are a lot of information, but the goal is to see if all of them, they have approximately the same range. As we overlap all the experimental semi-variograms, the cross one and the direct ones, then we can see that they are, you know, the range for all of them is pretty similar. Don't be worried about the partial seal or the nugget, as we know it can be different, but for the shape, you know, for the shape that is going to be the model, all semi-variograms has to be pretty similar. And this graph maybe can help. I'm not sure 100%, you know, it depends on each person, but maybe it's useful. Then I decided to add it, okay? And the last script related with the experimental semi-variograms is going to be to create a spreadsheet with that data, okay? Because, you know, sometimes if you have the data in a spreadsheet, you can manipulate the data more easily, and you can make the graphs like you want, you know, with Excel or OpenOffice. The alternative to manipulate the data, it's bigger, right? Then sometimes you want to have that data on an spreadsheet, and this one is the script for that one. Let's go to run this one and let's see how it looks like. Then structural analysis is 48. that is the omnidirectional experimental semi-variogram co-regionalisation table. Then we are going to add the data here. This one is good. Logarithmic with base 10. Lit here. Cutoff 1500. Lag 125. That's for the sync. And this one is for the lit. And then we can save the spreadsheet in a specific folder. I'm going to save in the number 9 this one here as semi-variogram. Semi-variograms. Then save, and then we can run and open the folder. Then it's going to be in number 9. Is this one? Let me refresh this one. Is over here. Then I'm going to open. It's going to be over here. Open as a copy, and here we have the information. Here in this column we have the number of pair of samples. Here we have the lag distance for each lag, and here we have the semi-variance. And here we have what is the cross-variogram, right? I mean, what is the semi-variogram? The first one, from here to here, is for the cross-variogram. This one is the direct for the lit, and this one is the direct for the sync. And then, as you have the data here, you can make the graph like whatever you want, right? There are a lot of different alternatives when you are using a spreadsheet like that to create the graphs, and that's up to you. Now it's time to see the model that we are going to fit on the experimental semi-variograms. Then I'm going to paste here the script, and we are going to call this script like 50 model experimental semi-variogram co-regionalisation, okay? Then I'm going to cut this one here, cut, remove these 2 lines, and I'm going to paste over here. Remember that is number 50, okay? Then paste, and let's see a little bit what we have here. We know about all this information. Also, we know about the libraries we are going to use. This one is to define the parameters and the layers. This one is for the cross-variogram we talked already. And this one is the script that we are going to use for the model. The important thing here is that the fit on the experimental semi-variogram is not going to be automatic, it's going to be manual. Then we have to put the exactly numbers we want for the partial seal, for the range, and for the nugget. And also we have to select the model that we want. And also with this line over here, what we are saying is that we are going to fit the same model with these values for all 3 variograms, okay? And that's very important because, as I said already many times, we want the same model and we want the same range, okay? And this one is just to plot the graph. And this one I put some limits for the axis just to make sure that we can see everything well. Then that's it. We can close this one and run that script. It's number 50. What is 50? Over here, 50. Double click to open, and again the target, the layer target is this one. This one is the layer auxiliary. The target variable is this one. The auxiliary is this one. Cutoff is 1500 meters. Lag distance is 125. The name of the variable is, the main variable is sync. The covariable here is lit. Then the partial seal, the model, we know we want to use the spherical, right? The partial seal, we are going to use the data that we get when we was analyzing the target variable, okay? That's the values that we get. Then I'm going to use these values to fit on the 3 variograms the same model. And this model, it comes from the target variable. That's the first approximation that we are going to do. You are going to see later that we have to modify these values to have a better results, okay? But at the moment, I'm going to use these values. Then for the nugget effect, I'm going to use 0.014. Then go here. Nugget effect is going to be 0.014. For the range 1162, range 1162, and for the partial seal we are going to add 0.112. Then here 0.112. Then, well, that's it. We don't have to add any extra information. Then just run. Then what we have here, the information related with the variograms. We saw already all this information. And what we have here, we have also the structure for each model. Okay, this one is the structure for the sink. This one is the structure for the lid until here, and this one is the structure for the cross-variogram, for the sink plus the lid. And as you can see, all of them has the same nugget effect because we add that information, okay? And all of them has the same partial seal, as you can see, partial seal, and also all of them has the same range because we add that information. Then we can go to see the graph, and this one is the graph. And as we can see, with that information, the fit is not that bad. It's really good. You know, in all three models, in all three experimental semi-variograms, the model fits really well. But what happened with these models, we are not sure if we are going to cover the conditions related with the linear model of co-regionalisation. Maybe this assumption it's not covering with this model over here. Then now we are going to use another script that is going to make any correction in these models in order to cover the assumption related with the linear model of co-regionalisation, in order to cover this assumption over here. And that's the next script we are going to see. Then create new script, paste. That one is going to be number 51 and is going to be model experimental semi-variogram co-regionalisation correction, okay? And here we have the same from here to here, that is the same as the other script, okay? But in this script we are going to add this new thing, okay? And this new thing is to fit the linear model of co-regionalisation. Then here we are going to add the cross-variogram, is this one, that is the experimental semi-variogram we have for the three, for the cross and the two directs. Also we are going to add the model that we created, is this one, that we saw already over here, is this model. You know, it's the same model for all three experimental semi-variograms. And also here we are going to add some specific parameters that we are going to talk about it. Then let's go to see the first one, fit method. Then you can make a search on Google. That's what I did, and I put here fit method gstat. And in this website over here you have the information. Then as you can see, when we added this parameter, it means that there are different ways that we can adjust the, let me show you here, this one, we can adjust the model on the experimental semi-variogram, okay? And all these methods are explained here. Then we can go to see the tiles, and here in the tiles you have a full explanation about how it works. You can read this information to have a better understanding of this parameter. Then in this case, in the case we are working, we are going to use the number 6. Okay, is this one. but you can use other methods if you think that is more adequate for your data. For the next parameter is this one over here. That is a correction that we are going to apply on the diagonal. In what diagonal? In this diagonal over here. Let me show you. In this diagonal over here, to have a stable matrix system, you know, to have a positive definite system here. Then if you are leaving one, well, let me show you on the website, it's going to be better. Then what I did is put this script, fit linear model of co-regionalisation. Then I get the function over here, and the definition of this parameter is over here, right? Then if you put just one, you are not going to make any correction. But if you want to make corrections, you have to add this value over here. Then that's what I did in this script, to put that value over here in order to have the system positive definite, okay? That's the goal of this script over here, to have a positive definite system that is necessary to apply co-kriging, okay? Then this one is just for printing the graph, and now we can see the results. Then let's go to save this script, then cut over here, remove these two lines, save with that name is going to be number 51, save, then close, and let's go to run that script. 51 structural analysis, and 51 is over here. Double click to open. This one here is good, this one here, this one here. We are going to add the same parameters, 1500, 125. Again, here is sync. Again, here is lead. And for these ones, we are going to add the same values here. Partial seal is this one, 0.112. Model is going to be spherical. Spherical range is going to be 1162, and the negative effect is going to be 0.014. Remember that these values, it comes from the model that we fit at the experimental semi-variogram for the target variable, that is the log 10 for the zinc concentration, okay? That was the first structural analysis that we did in this lesson, okay? Then we have to add these values here, and the software is going to make the correction automatically in order to have a valid linear model of co-regionalisation. I mean a positive definite, okay? Then run, and here we have the final values. Then if we compare these values, that is the correction, with these values, we're going to see that the values are different. What is still the same? The range. The range is the same because the range has to be the same, okay? The only thing is changing is the negative effect and the partial seal, as you can see, okay? Is changing. Here and here we have different values. But with these values over here, it is guaranteed that the system, you know, this system is positive definite. That is what we need to do co-kriging. Then we can see the graph over here, how now the fit is different. Let me make this one bigger. Okay, now the fit, if we compare with the other one, the fit is changing, okay? And this one is the one we want. Also, I calculated the matrix determinant for each structure to demonstrate that they are positive definite. Let me show you. here. Here we have the values. These values are the same as these ones here. Let me show you. Over here are the same as these ones. No. The same as these ones, okay? This one is the one with the correction. These values over here are the same as these ones. And with these values, I calculated the matrix, the determinant for each structure, and I get a positive number, okay? It means that the matrix is a positive definiteness. It's not necessary to verify this one, right? Because it is supposed that the software provide the matrix system that is positive and definite. But if you want to do it, if you want to make the double check, that's good, just to make sure 100% that everything is okay. Remember that the first term is the semivariance for the sync. The second term over here is the semivariance for the cross-variogram. In this case is sync lead. This one is symmetric, but in this case is lead sync. And this one is for the lead, okay, the semivariance for the lead. And here we have the structure related with the nugget effect, and here we have the structure related with the spherical model. Now the next step is to see how good is the model that we created, the model of co-regionalisation. Then to do that one, we are going to do a leave one out cross validation for the Cokriging, okay? Then I'm going to paste here the script I did already. Then I'm going to cut this one here. This one is going to be script number 52, and the name is leave one out cross validation omnidirectional co-regionalisation table. Okay, we are going to get the data related with the cross validation. Then cut, remove these two lines, and save. Paste here. This script it's a little bit complex, but you know, we was talking about the cross validation in the previous lesson. You know, it was the lesson 8 of the third geostatistic course, and it was cross validation for leave one out cross validation and key fault cross validation. And in that lesson I explained everything, okay? I don't going to say anything here because it's going to be repeat the information. Then if you want to see how this script works and everything related with this script, you can check that lesson over there, because the only thing is changing here is just these values, and that is related with the experimental semi-variogram that we want to do the cross-variogram, and also the model, that is the model related with the co-regionalisation. And also here, to get the values, some parameters related with the cross-validation, we use a different script, but the rest of the things are the same, okay? And I don't want to take some time to explain what I did already at the previous lesson. Then we can run now this script. I'm going to close all of these ones. And it's number 52, I believe. Double click to open. It's just leave one out cross validation. Then number 50, 155. Here adding the same data again. Name of the target variable is sync. The next one is for delete. Then the cutoff is 1,500 meters. Lag distance 125. Here we have to add again the values related with the target variable, okay? The first structural analysis that we did, okay? Then the partial silhouette was 0.112. Model is spherical. Range is 1162. The partial seal is 0.014, and we can save that one because this script is a table, okay? Then we can save here as leave one out cross validation, leave one out cross validation for Cokriging. Then save, and then we can run this script. And what we have here, several parameters related with the residuals, and also again the structure of the model. Then we can go to open that spreadsheet. Is this one over here? Open. This one I can close. Okay, open, and I'm going to open as a copy. And here we have the parameters associated with the leave one out cross validation for the model of co-regionalisation. Then we have the column for the predicted values according to that model for the zinc concentration. Then we have the variance also for the zinc concentration. We have the observed values, that's the values that we get at the samples. This one is the residual values. The residual values, as you already know, because we already explained at the previous lesson, is the difference of the predicted values with the observed values. This difference is going to give us the residual values. The set score is the residual value divided by the standard deviation. Faults is the number of faults we have. In this case we have 50 because it's leave one out cross validation. And here we have the coordinates. Again, if you want to have a full understanding of this table, my recommendation is to watch the previous video tutorial related with the lesson 8 for the leave one out cross validation. I decided to add this script because I believe it is pretty nice to have the data in an spreadsheet, because you can manipulate the data with another different software, like for example OpenOffice or Excel. Then you can make any graph as you want with all this data over here. Now we're going to close this one and move to the next script. This one is going to be the last script of this lesson, and also the last script of the course, okay? Based in this one, what we are going to see is the graph related with the leave one out cross validation for the omnidirectional co-regionalisation, okay? Then cut. Remove these two lines. Again, if you want to know how this script works, just check the previous lesson. Save. We have everything is the same. The only thing is changing again is this section over here related with the experimental semi-variogram, the model, and also we did some modifications related with the parameters and the layers, because we are working here with two different parameters, but the rest is the same as we was using at the cross validation for kriging. Also this one is changing. Then close this one and let's go to run this script. It's number 53 over here. Double click to open. Again, this one is this layer, this one is good. Sync lead cutoff 1500, lag distance 125, partial seal 0.112, model spherical, range 1162, nugget effect 0.014. Even we are adding these values over here that are related with the structure of the zinc concentration with the logarithmic base 10. It doesn't mean that we are going to use these values because the script has incorporated the correction, okay? We are using these values as initial ones, but the script is going to correct these ones and is going to add the proper values related with the structure, okay? The number of bins is for the histogram related with the residuals, then it's going to be 7 because we have 50 samples, and the title of the graph is going to be leave one out cross validation for Cokriging. And that's it. We can run and see the results. Then here we have the structures. As I said previously, these values are different the one we introduce over here, okay, because the script is doing the correction. Also here we have a different values related with different parameters associated with the cross-validation. The one we are going to use is the root mean square error. And as you can see, this value here is really good because it's 0.06. As the value is close to 0, better is the model. And for this kind of value, 0.06, we can see that the model is really good in this case, okay? Then let's go to see the graph. And let's go to make this one bigger. Also, again, for the interpretation of this graph, my recommendation is to see the previous video related with the cross-validation. The maximum difference that we can find between the predicted value and the observed value is the residual value, and in this case is 0.2. This one is a really good value, indicating that the model is really good. Also, the residuals is following a normal distribution. We have some values here, but you can see the values are 0.2. It's not really big. And these values at the tail is going out of the line. That's pretty normal. Is all these values over here, and this one is this value over here. But most of the values are 0. That's really good. And look at this one. This is amazing. We have almost the red line with the black line, indicating how good is the model. Now what I'm going to do is compare the cross-validation, the leave one out cross-validation for kriging with the leave one out cross-validation for co-regionalisation to see what is the improvement of the model, okay? Then let's go to run that script. It's going to be, let me check. This one over here, leave one out cross-validation, omnidirectional graph. Double click to open, and remember that this script is part of the lesson 8 of the third course of geostatistics. And here we are going to select just the 50 samples for the zinc concentration. The parameter again is going to be the logarithmic with base 10 for the zinc concentration. Cutoff is going to be the same as before, also the lag distance. And here we are going to add the values approximately, because in this script, the model is going to be fit automatically, okay? Here is saying seal, but that is wrong because it has to be partial seal. And the partial seal here is 0.112. The model, we want the spherical one. The range, we want also approximately. We are going to add 1000, and the nugget is approximately also. Number of beans, as we have just 50 samples, I'm going to put 7, and the name of this one is going to be leave one out cross-validation for kriging. Now let's go to run the script. Again, if you want to have full understanding of this script related with leave one out cross-validation for kriging, just check the lesson 8, okay? That's the previous video we did. Then here we have several parameters related with the leave one out cross-validation. The value that we are going to use is the root mean square error, and as you can see here, this error is 3 times bigger than the error that we get when we was using leave one out cross-validation for co-regionalisation, because the value here, it was 0.06. Then the error here at the leave one out cross-validation for kriging is 3 times bigger. Then you can imagine that we are improving a lot, right? Also, as I said previously, the model here is fitting automatically. We have these values, but the values we add were these ones, but the model is fit automatically and give us these values. And these values were the values that we put over here, because in this script the model is not fit automatically. Okay, we have to put first these values, and then the software is going to make the correction, okay, for the best model for co-regionalisation. This is the difference between these two scripts, okay? And also now we can see the graph. Double click to open. Not this one. I'm not interested in this one. I'm interested in this one. Let's go to make the screen bigger. And as you can see now, the residual values again is 3 times bigger if we compare with the other one. With the co-kriging we have 0.2, but with the kriging we have 0.6. The errors associated with the residual values are 3 times bigger. The distribution of the residuals, they are pretty normal, that's good. But if you can see the model, there is a big differences. Let's go to compare both together. Here you can see how amazing is the model of co-regionalisation. You can see the dogs comparing the predicted with the observed values. They are making a almost a straight line, you know. But here the lines are pretty separated, and this model is really good compared with this model. Then the improvement with the model of co-regionalisation is so good. You know, we improve the results a lot, because the residual values that we get in the Cokriging model are 3 times smaller than the values that we get at the kriging model. Also, as we saw, the residual values, I mean the root mean square error for the co-regionalisation model, as you can see over here, is 3 times smaller compared with the kriging model. Then this one, it's a really good example where you can see that the model of co-regionalisation works and improve a lot the model. You know, if we compare the kriging model with the co-kriging model, what we can see is that the improvement of the results with the co-kriging is so big. Well, that's it for this video. Thank you very much for watching, and see you on the next course.